All right, so today we're going to be talking about something that you've studied in past math courses, but we're going to be really doing a lot with making what you've previously learned more precise and learning things and how to make our life easier using StatCrunch. So we're talking about scatter diagrams and correlation. So when we are talking about that, we need to make sure we know the difference between univariate and bivariate data, which, knowing the prefixes uni and bi, I think you can probably figure out what the difference is. So univariate data is data in which a single variable is measured for each individual. So remember, individuals are what we're collecting the data from. Doesn't have to be a person necessarily, but if we're only collecting information about one single variable, that's univariate data. Bivariate data is data in which two variables from a single individual are measured. A scatter diagram, which in previous math classes you've called a scatter plot, is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the diagram. The explanatory variable is plotted on the horizontal axis, so that's your input, your independent variable, and the response variable is plotted on your vertical axis or your y-axis. That is your dependent variable. So your response variable is dependent upon the value of the explanatory variable. So sometimes students have a hard time deciding which variable should go in which place. If you're having trouble, think about what I've put here. The variable that you want to predict should be your dependent variable. That should be the one on the vertical or the y-axis. So in Algebra 1, and really honestly before that, you have talked about correlation and association. So a positive association is when you have two variables that are linearly related. So this only works if their relationship resembles a line. It's a positive association if the value of one variable increases when the other one does also. So meaning as one goes up, so does the other one. It's a negative association if one variable is increasing. So the value of one variable increases, the value of the other variable decreases. So we have positive and negative association. Again, we should only be talking about these if there appears to be a linear relationship. So speaking, excuse me, of linear relationship, we measure that with the linear correlation coefficient, and that is a measure of strength and direction. So it tells us two things: the direction of the linear relation and the strength of it. And this is for quantitative variables. Remember, one of the things that we've stressed in this course is what type of graphs are appropriate for qualitative data and for quantitative data. So here we're adding one that you could put in your list for quantitative data would be a scatter diagram. So our symbol for linear correlation coefficient, this Greek letter, it kind of looks like a lowercase p-ish. It's not. I think that's maybe a row, a lowercase row. But anyway, this is the symbol for correlation coefficient in a population. We almost honestly never use this one because almost always we are looking at a sample and R is the variable that we use for that. It's a lowercase r, not an uppercase R. This is the formula that we would use to calculate it, just so you know. I am not going to ask you to calculate that by hand. You can see that there's an awful lot of steps because you have to do every xi minus x bar, every yi minus y bar, divide by their standard deviations, add them all up. It's a lot of by hand work. So we are going to use StatCrunch for this, but I at least wanted to show you what the formula was, just in case you would ever need to do something by hand. On the linear correlation coefficient, the values are between -1 and 1. And you've talked about correlation coefficients before, whether you remember or not. I know for sure it's in Algebra 1. So I've given some pictures here of different types of relationships and the R values that would be associated with them. So you can see an R value of +1 is a perfect line in a positive direction. -1, perfect line in a decreasing direction. So you can see, like, when we go down to 0.9, okay, it's not a perfect line, but very, very linear. Then you can see, okay, we're moderate here. Where's the R? About 0.4. Then you can see this is just a mess of dots. You can't see a linear pattern in that at all. Over here on H, just because there's a pattern doesn't mean that it's linear. This pattern is quadratic. So both G and H should have an R close to 0, meaning that there is no linear relation. So you can see that, if we have an R that's, somewhere between maybe 0.4 and 0.9, that it would be closer to the line than what we see over here, but maybe not as tight together as what we see in B. When we get lower than 0.4, we really start to not see much of a linear association. We are going to learn various tests for critical values. So I'm going to teach you how to use a table for finding critical values to test. This is table 2 in Appendix A. So you are going to need to go to the appendix in your text in order to look for the appropriate critical values. So we find the appropriate critical value in the table. Then we calculate the value of R. If the absolute value of R is greater than the critical value, then we say, yes, a linear relationship is appropriate. If the absolute value of R is either the same as the critical value or less than the critical value, then we say, no, there's not enough evidence to say that a linear relationship exists. Remember that even if we are saying that there is a linear relationship, that they have some correlation, that is not the same as causation. Just because there's a relationship does not mean that one of those variables is the cause of another. I've also got your StatCrunch directions here for you. Again, remember that it's important that you know which variable is the explanatory and which variable is the response. So response is your dependent variable. That's what we're trying to predict. It's pretty simple. You just go to graph, you go to scatter plot, and click compute. On correlation coefficient, this is part of summary stats. If all you need is R, you can very quickly get that value as well. So make sure that you know and kind of have an idea of these different correlations and the R's that would be associated with pictures because you may be asked to estimate. It may give you a scatter plot and say, what would you expect the R value to be on this scatter plot? So knowing those values is going to be an important thing. All right, so let's start looking at some of the types of questions that you might be asked here. If you would like to follow along in StatCrunch, get yourself logged in, and then the data set that I'm using here, obviously you need to scroll down to Chapter 4, Section 1. This is from problem number 37. So if you're wanting to follow along in StatCrunch, that's the data set that you should upload into your StatCrunch sheet. So an engineer wants to determine how the weight of a car affects gas mileage. The following data represents the weights of various domestic cars and their gas mileages in the city for the 2015 model year. A, determine which variable is likely explanatory and which variable is likely response. So this is what you are asking yourself. You are asking because we're trying to determine independent and dependent. So are you saying that the weight of the car depends upon its gas mileage, or are you saying that the gas mileage depends upon the weight? Hopefully in your brain, you just said the second one, that gas mileage is going to depend upon weight. Also, we're not usually very interested in predicting the weight of a car, but we might be interested in predicting its gas mileage. So our explanatory variable is going to be the weight. And the response variable, the one that we would be interested in predicting, is going to be the gas mileage. Draw a scatter diagram of the data. So you do not need to do this by hand. I would very strongly suggest that you use StatCrunch for this. Remember that in the homework, you can, print screenshots and send me screenshots of the StatCrunch. You do not need to write them out by hand unless you are really, really wanting to do that. But I think it'll take you much less time to use StatCrunch. So I'm going to go ahead and go over to StatCrunch. So here is our data. So I'm going to go to Graph, and I'm going to go to Scatter Plot right here. Maybe if it will let me select it. Come on, little buddy. There we go. All right, so my X variable, meaning my independent variable, is going to be the weight. My Y variable, the one that I'm interested in predicting, is going to be the miles per gallon. So then I am wanting to display points. You can choose different point types if you want. Filled circles are generally what we want. If you want them to be thicker, you could certainly change the point size. We don't need any dividers. You can change the color scheme if you want. You do need to type in labels and a title, just like we always do. So we are going to put our x-axis label as pounds and our y-axis label as miles per gallon. The title is weight of domestic cars versus, typo, gas mileage. Okay, so then I can click compute. Let me drag it over so that you can actually see it. So here we can see everything labeled. We can see a dot that represents each of those data points that we had. So this is very good. It takes much less time because if you're doing this by hand, you have to come up with a scale, all of that. So much, much easier to do in StatCrunch, takes a lot less time. So there's our answer to part B. We've got our scatter diagram. Part C, compute the linear correlation coefficient between weight of a car and its city MPG. So again, that's in summary stats. So if I go to stat and summary stats, and I am going to correlation, and so we are selecting both weight miles per gallon, and then none of these need to be filled in, so we can click compute, and it spits out for me. And again, remember, when you are printing or screenshotting or whatever you're doing with stuff from StatCrunch, move these little windows around. Get them all in the same picture so that you don't have to work as hard. Here is my correlation coefficient. So I think usually we carry 4 decimal places on these. So we're going to say negative 0.8416. And so going back to my notes, and it is important that you say R equals. This is obviously a sample and not a population. So negative 0.8416. So then D, does a linear relation exist between the weight of a car and its city MPG? Unless we are unable to, whenever it asks, does a linear relation exist? This is not just guessing. We have to actually compare the absolute value of R to the critical value. So this is what I was talking about on the front, where you need to go to the Appendix A and Table 2. So I'm going to switch over here. So in my text, here's where the appendix is. It's right above the answers for tables. You can see it says Table 2. It's based on sample size. So when we look here, the number of data pieces that I have from the cars is 10. So I'm looking for n equals 10, which is right here, and the critical value is 0.632. So for n equals 10, critical value is 0.632. And so the absolute value of R in this case would be 0.8416. Because absolute value changes it to positive. That is greater than the critical value, which means yes, there is a linear correlation. And this is our proof here. We don't just say yes, we have to prove that it's a yes. Part E, suppose that we add the Ford Fusion hybrid to the data. It weighs 3,639 pounds and gets 44 miles per gallon. Redraw the scatter diagram to include it. So go back to my data sets. I'm going to switch so that this is over here. So now I am going to type in Ford Fusion hybrid, and its data point is, let's see, what did it say? 3,639 pounds and 44 miles per gallon. So now I go back and I do the exact same thing that I did before. Scatter plot, X variable weight, Y variable miles per gallon. And So adjusted weight versus gas mileage. And x-axis label is still going to be pounds, and y-axis label is still going to be mpg. Compute. So if I compare the scatter diagrams, you can see this guy right here is my new data point. It does not really seem to fit with the rest of it. So that's what I would say for what we notice. And again, look at how I'm just dragging everything over. You can fit all of this in the same screenshot when we're done with the problem. So what am I going to say? The new point doesn't seem to fit the trend. Recompute the linear correlation coefficient. How did this new value affect your result? So again, I'm going to go back. I'm going to go stat, summary stats, correlation, select both of those. None of this stuff is needed. I can click compute. Look at the huge difference here. So remember how we said that anything kind of below 0.4 or higher, on the negative side than 0.4 was probably not going to be a correlation. Look at this huge difference with that data point added in. So I now have n equals 11. So if I am recalculating my critical value, n equals 11, it does drop it to 0.602, but n equals 11, CV equals 0.602. In this case, my absolute value of R is now 0.3309, I think it said. That's now less than the critical value. So now there is no linear relation with that data point added in. So new data points don't always change my outcome, but sometimes they do, as we can see here. So we've practiced that R and whatnot twice. Why does this observation not follow the pattern of data? So again, questions like this in your homework, you might have a different answer than I do. But for me, I'm going to say because it was a hybrid model and shouldn't be compared with traditional vehicles. If you want to compare gas mileage, you should compare the same type if you're wanting to see if there's a linear correlation here. Now, if you're just comparing to see what gets better gas mileage, that's different. Then obviously we can compare hybrids to traditional vehicles, and we're going to see that hybrids, have much better gas mileage. But here we're trying to compare weight with gas mileage, and these are two totally different types of vehicles with very different gas mileages. So this would be one explanation as to why that would happen. All right, so hopefully that all makes sense. You should be set up for your practice problems. And as always, let me know if you have questions.